Yeah, my name's Adrian, and I've been with Metal Earth since the beginning, um, 7 years ago, 8 years ago. And I'm going to present my work on the last chapter of my PhD thesis here, which is looking at the fluids in the Quetico basin. How do we produce these fluids that we've been talking about a lot? So we've been talking a lot about orogenic gold deposits, and one of the things that I find fascinating about orogenic gold deposits is that it seems like they share characteristics throughout time, whereas in other gold deposits, there's some sort of temporal variation through Earth's history, because most of these deposits, Archaen or Phanerozoic, they form at major lithological boundaries, are typically in green schist to lower amphibolite facies, and the vein sets are usually quartz carbonate and sometimes tourmaline. And the carbonate is quite characteristic of these deposits. And so we think that these were produced by very similar fluids, so low salinity fluids, 5 to 7 pH, and carbon around 10 to 30%, which is quite high. And the sulfur is really going to be pretty low in these fluids, and we'll kind of see why. And of course, one of the main important things is that gold is transported or thought to be transported as a reduced sulfur species. So one of the main model for sourcing these fluids is the metamorphic devolatilization model, which really mostly initially came from the devolatilization of graphitic carbonaceous sediments in modern graphitic belts. And it's kind of an elegant model because it allows us to have one mechanism really for deformation, the production of fluids, the release of golds, the breakdown of pyrite. All these things can happen by autogenetic processes. And so that's kind of why a lot of people gravitate towards it. So one of the things about Archaean rocks and Phanerozoic rocks is that they're lithologically they're quite different. Most of the belts in the Phanerozoic are, of course, graphitic sediments dominated, whereas in the Archaean, we're dealing with hydrated mafic rocks as a potential source. And so those were kind of the initial models that were put forward for the production of fluids in those belts. But more recently, with the work of Pitcairn, we've started talking about siliciclastic sediments, so the Quetico turbidites, the Pontiac turbidites, as a potential source. And not only is it as a good potential source of gold, which we see losses of gold in these big sedimentary subprovinces, but we can actually look at those the metamorphic assemblages in these rocks, the reactions in these rocks, a lot easier than we can with volcanic rocks, just based on their politic assemblages. So all this to come to the idea that when we're dealing with orogenic deposits, a lot of the times we think about, this must be a sink process, because in metamorphic devolatilization, that happens to all sediments. So where it's such an elegant model, it also doesn't explain why there's differential gold endowment. So a lot of the times we invoke, there must be something different in the sink and the structural history. But what if we dig deeper and kind of look at, is everything really the same when you go down to the source? So my area is the Quetico subprovince, big turbidite basin that deposited around 2.7 billion years ago. And one of its great characteristics is that it preserves metamorphic metaturbidites from green schist to granulite facies, exposed along 1,200 kilometers of strike length through the central western Ontario. And it's a symmetrical distribution. So you have both sides, you get these green schist facies rocks. So it's a lot of area to play with, a lot of things to look at, and there's variable gold endowment along the Quetico because it's such a long belt. Most of these deposits are going to be in the greenstone area in Beardmore Geraldton, and then kind of the rest of the Quetico to the west, especially. There aren't really any deposits there to speak of, so we can test any potential differential endowment along the strike. So for methods, I did field work over 2 summers and visited about 600, 700 outcrops, lots of samples collected. Me and Diogo collected over 250 samples from these transects. And so it gives us a big data set to look at the petrography differences or variations in petrography in whole rock chemistry. And so, yeah, grade-related variations is, I'm going to talk about them, especially for the major elements, and we were able to have a big data set for hydrogen, carbon, and sulfur content, which we get in the metal earth package, complete characterization package by the combustion furnace infrared spectrometry method. And then all this is kind of pushed towards phase equilibrium modeling. And so we're using quite a large system here. I think it's one of the first studies that have used carbon and sulfur along with the MN-CKF MASH system. So it's quite a large, complex system. And we're basically doing three things with it. We're trying to determine the PT vectors of the rock, the PT history of the rocks, what's the stability of pyrite and pyrrhotite and the oxides, because this has quite profound effects on our predictions. And then, of course, how much fluid is being generated, what's the composition of the fluid, at what time. Okay, so in the Quetico, we have chlorite through biotite, garnet, staurolite, andalusite, cordierite, sillimanite, all the way up to orthopyroxene zones. And so this map kind of shows the distribution of the isograds in the Dog Lake area. And one thing that's kind of important is that we have quite a bit of variability in the protoliths. So we have, basically I've characterized three types of protoliths based on calcium and potassium content in these rocks. So we have quite a bit of different mineral assemblages, as you can see on that map there. So to summarize some of the main textures for the silicates and oxides, we have chlorite muscovite, epidote at lowest temperatures, and then you get biotite in, where first you lose K feldspar, and then you'll lose muscovite shortly afterwards. Garnet and staurolite come in, and by that time you lose most of the chlorite. So the muscovite and chlorite are kind of the most important ones because this is really where most of the fluids are going to be generated during the loss of those phases. And then we also have, at a bit higher grades, cordierite forms by staurolite breakdown. And I've included this oxide paragenesis that Diogo was talking about, the titanite and rutile at low grades, ilmenite, and then a little bit of magnetite at the very highest grades. So into the stuff that is maybe a bit new, the Quetico has some carbonates in it at the lowest grades. It's in the chloride zone. Usually these are found kind of altered plagioclase clasts. So you pour some acid on them and you can see that the clasts in there are preferentially reacting to the acid. And then you can also see that at a bit higher grade you actually get discrete grains of calcite that appear in the matrix, sometimes dismembered veinlets as well. But beyond the biotite zone, the rocks no longer react with HCl. Calcite is gone from the rock. For sulfide, Diogo talked more about this, but we have pyrite and sometimes pyrrhotite at lowest grades, and then pyrite disappears, and you get pyrite or pyrrhotite plus pyrite 2, which is potentially a retrograde pyrite. We're still kind of seeing what that is. But as Diogo showed, that pyrite to pyrrhotite reaction is what's releasing gold. So we really want to be able to track what pressure temperatures that's happening at. Okay, for major elements, as I mentioned, there's quite a bit of variability in the calcium and aluminum versus aluminum and iron. And so what this means is that these are typically biotite-rich, muscovite poor peelites compared to the typical worldwide peelite. So that's going to have some impact on the phase equilibria stuff. And so here we can also see that I've plotted some of those major elements with grade. So these are the different zones as we're increasing grade. And so you do see a bit of variation. You get more of these politic compositions, but really that's probably to do with the initial basin architecture rather than any sort of metamorphic mobility. But with the volatiles, it's a bit more of an interesting story. So we have the hydrogen, carbon, and sulfur whole rock plotted, and you can see that really right off the bat from the chlorite to the garnet zone, you get decreases in water, in H2O. There's also quite a sharp decrease of carbon right after basically the biotite ice grad, just as we see in the textures there. But sulfur is really flat. There's just the only variability we see is probably layer to layer of variability that we kind of expect in sedimentary rocks. And as in both the major and volatile elements, there's not really any east to west variability that comes out in the data. So really the protoliths seem to be, at least appear to be very similar along strike. Okay, so these are now into the modeling. I'm not going to go too much into the details of how we did the PT vectoring in this, but here we're able to reproduce the observed assemblage for these two samples, and when we combine that with the garnet chemistry and the biotite and titanate chemistry, biotite and plage chemistry, we're able to kind of come up with an idea of what the PT vector for the rock. So in the garnet zone sample, we go from about 5 kilobars at the garnet inline, 5 kilobars, 500 degrees Celsius, up to 560, 6.5 kilobars. So that's really just kind of a normal burial path. And then at higher grades, we get a bit more complicated stuff. Kind of as Isaac showed, you have a bit of a decrease in pressure with increasing pressure initially. And then to get into the Andalusite and cordierite zone, you need to basically decompress this rock. And so you can decompress it to about 3 kilobars or lower potentially. So overall, this represents kind of a clockwise PT path for the Quetico. And we're going to use that as just a generalized PT path for the rocks. So for the oxidation state, when in Therag Domino, which is the program that we're using, you have to adjust the oxidation state, you have to basically add a bit of oxygen or reduce the oxygen in the system, and we call this adjusted oxygen. So that's the x-axis here. It just represents more reduced rocks down at the left end, and then slightly more oxidized rocks at the top end. But really, this is only ferric iron values between 0.01% or 0.01 and 0.2. So weakly oxidized rocks in general. And one of the things that's kind of key here is that the pyrite and pyrrhotite stability field, or the transition field that I've kind of labeled here, is quite sensitive to the oxidation state at kind of relevant temperatures, 350 to 500 degrees C. If you increase the oxidation state by just a little bit, to a composition of 5%, 6% ferric iron, you're going to basically stabilize pyrite to much higher grades, and pyrrhotite won't come in at all, which means that your gold won't be available to the fluid. So very subtle changes, at least based on what we see here, can result in very different pyrrhotite transition temperatures. So that was for one sample, the chloride zone sample. And this is for another peelite sample. And you'll notice that the pyrite to pyrrhotite window is thinner. And that's mainly because the sulfur content is quite low in this rock, 0.07 mole percent, versus the other one was about 0.35. So decreasing the sulfur content actually makes that window smaller. So even though maybe you don't have as much gold in that rock because there's not much sulfide, that window is a lot smaller, so it may actually be more favorable for an efficient pyrite 1 breakdown. Okay, so for the fluid, this is another PT sections. On the left, you have just kind of a simplified pseudosection with the pyrite to pyrrhotite transition and the garnet and garnet in, calcite in is also shown. And so this is the generalized PT path from those couple samples that we did thermobarometry on. And you'll notice that the pyrite pyrrhotite transition happens pretty early on based on the oxidation state that we chose. We chose that because it most closely reproduces our oxide assemblage. But from basically 300 or 350 to 400, you get kind of an extended period of pyrite to pyrrhotite transition. And the peak fluid in this rock comes at about 500 degrees Celsius, 480 to 500 degrees Celsius. And this coincides with the loss of both calcite and muscovite at the same time. So that's a major CO2 and H2O releasing reaction. And then once we get into the later, beyond that, into the isothermal decompression part, we're not really having much water kicking around anymore because this semi-peelite does not have anything left, or just a little bit of chloride, I guess, at the end there. And then on this right diagram, we have the composition of the fluid, so the carbon composition and the sulfur composition. And you'll notice that during this pyrite to pyrrhotite transition, there's actually very little increase of sulfur into the fluid. So the sulfur is not going into the fluid during that reaction. It's being used to produce more pyrrhotite. And I'll talk about that later. The CO2, on the other hand, does go into the fluid. There's no other phases for it to go into, so we get up to about 35% CO2, which is kind of right in the sweet spot there. This is the same thing, but for a peelite sample. So now we're expecting to get porphyroblasts, staurolite, and sillimanite, cordierite at higher temperatures. You'll see that this has the pyrite to pyrrhotite transition is slightly closer to this 450 degree first pulse, fluid pulse, and that window is smaller. Once you get the peak fluid for this rock, though, is at the staurolite in, and that's where you get the simultaneous release of, or simultaneous breakdown of chlorite and muscovite. So compared to the other one where muscovite was breaking down at lower temperatures, now muscovite is stable until you get to staurolite in, which is around 550 to 600 degrees Celsius, in that range. But this is actually very much a H2O pure fluid because there's no more calcite in that rock so it's just an H2O fluid, and similar to the other sample, we have a very, very low sulfur in the fluid as well. So now that was in a fixed bulk composition, in a pseudosection needs to be fixed bulk. We can basically fractionate out that fluid along that PT path that I showed, and we're going to see basically the same, pretty much the same results. The only thing that's going to change is really the composition of the fluid will be a bit more realistic, I think, because you're not carrying all that fluid with you as you go through prograde path. But again, the main reaction here is going to be that for the semi-peelite is going to be the muscovite out, calcite out at 480 degrees Celsius, 5 kilobars. And that's the composition of the fluid there. Then for the peelites, you have one pulse at that muscovite, the first biotite in, muscovite out, and calcite will go out there too. So you do get a fluid pulse in the peelites there as well. But then this staurolite in pulse is about the same amount of fluid, or is predicted to be the same amount of fluid, but this one is less clear in natural observations. If I showed that basically after the biotite or the garnet zone, you don't really see any losses in water anymore. So, and there's other reasons that this staurolite in reaction might not be as reproducible in natural observations, but I won't get into that too much. So, as I mentioned earlier, one of the interesting things about doing this modeling is that we typically think of the pyrite to pyrrhotite transition as a desulfidization reaction, but in reality, when you have rocks that have a lot of iron in them and very little sulfur, the sulfur is not going to go into the fluid because it's sulfur is a siderophile element, so it wants to go into these iron silicates. So instead, oxygen is liberated and goes eventually into the oxide, which is why we have that dependence on oxygen fugacity for that pyrite stability. So really, the sulfur liberation is just restricted to this kind of inefficient breakdown or the different activities of H2S and H2 in the fluid, which really doesn't involve that much H2S in the fluid. So what does this mean for our fluids? What's for our source factors? Well, I think it's clear here that a TX window might be actually more pertinent than thinking about a PT window. If you change a different gradient, you might have pyrite pyrrhotite coming in at slightly earlier pressure or slightly earlier temperatures, or maybe a bit more fluid produced at that time. But I think what's more important is actually getting the right bulk composition, because if you have very subtle variations in oxygen or even in sulfur, it'll change the reaction history. So I've kind of created a bit of a diagram here that shows kind of where the Goldilocks zone is you'd expect for the right composition to produce a really good COHS fluid at the time of pyrite breakdown. And so if you have too much oxygen in the system, pyrite is stable up at to 500, 600 degrees Celsius and muscovitis. And you've basically missed the boat. The fluid is lost, and the gold doesn't go with it because it's still in pyrite. So that's a red. If you have two reducing conditions, then maybe you get pyrite out too early, 300 degrees Celsius before the fluid pulse. So maybe it just goes out with a trickle, and you don't have time to form big crustal structures for the fluids to go into. So probably not the best. But in the Goldilocks zone, where you have 3% to 5% ferric iron, you're looking at you're going to get pyrite out at the right conditions near the fluid pulse. And then I talked about the importance of the protolith. If you have a protolith that's too enriched in in potassium and in aluminum, well, basically you're going to get the fluid out at storolate. So the best fluid, or the biggest fluid, will happen where muscovite out and calcite out go out at the same time, which is really in the more calcic protoliths, which happen to be the more abundant rock type in the Quetico as well, either way. Okay, so to summarize, we have a clockwise PT path through our green schist amphibolite facies. The major pulse in semi-peelites is going to be the muscovite out biotite in reaction at about 450 to 500 degrees Celsius. And pyrite breakdown doesn't really add any sulfur to the fluid based on our whole rock and our phase equilibrium modeling. And the most favorable conditions then might be more related to the bulk composition of the rock, the oxygen, the sulfur, the CO2. All these things kind of have to be within the right window in order to get the rock to release gold at the fluid, the big fluid pulse. Thank you.